Corey O'Connell for being here today. He is the Director of
My
Process.
apologies. I'm sorry.
You're fine. You're fine. We're just getting started, Dr. Wilson. I'm glad you're here. We miss seeing you. Dr. Corey O'Connell is the Director of Process Development for Special Metals Corporation, where he leads key research and development activities in manufacturing and new technology exploration for global operations. He's a Michigan native and a Huntington resident with his wife, Dr. Lynn O'Connell. Since 2014, he earned his PhD in metallurgical engineering from West Virginia Tech University. He provided a fascinating positive overview of the long history of the special metals, which is now part of Precision Cast Parts Corporation, which has other facilities in Connecticut, England, and Australia, and is the successor to the International Nickel Corporation, a major force in Huntington for nearly a century, known as INCO, or the nickel plant. With its early creation of Monel Metal, superalloys developed at the nickel plant have been critical in products from modern steel bridges to golf clubs, soup cans, and gas turbines. Inconel alloy 718 remains the most widely used nickel alloy. SMC in Huntington is now the largest integrated manufacturing site in the world for producing nickel, cobalt, and other superalloy forms. More than 85% of the critical alloys used today in the aerospace, chemical, energy, and power industries were developed by Special Metals Corporation. Nickel alloys are invaluable for their thermal capacity, corrosion resistance, conductivity, and I'm going to say this wrong, ferromagnetism. From coal-fired power plants to oil and gas appliances and even solar energy. SMC alloys are vital. The future is bright for SMC as it continues to serve a diverse customer base, and the company is well positioned for years to come. Dr. O'Connell is described an invigorating atmosphere where experienced employees and high technical capabilities are invaluable in developing new products and processes. SMC and PCC are now owned by Berkshire Hathaway, whose long-term focus has reduced pressure to respond to short-term shareholder concerns. And thank you, Dr. O'Connell, for being here, and I'm going to turn it over to you.
Well, I appreciate that introduction. Thank you very much. Yeah, it's a pleasure to talk to you guys. Before this, I kind of dug on the internet and saw a little bit about this program, and it's actually, I didn't know it existed. So it's awesome that Marshall fosters this type of program. And I actually know some people that I think would be interested in it. So
send them our way, please.
Yeah. So let me share my screen real quick. Let's do that. So I think that should have come through the slideshow mode. Hopefully it doesn't. Yeah, okay, so let me see if I can hide the thumbnail. I am not a professional Zoomer. As you can see, I don't have professional lighting or anything like that. So
we aren't either.
But again, thank you. And I'm calling the talk the nickel plant in quotes and its significance. As we started the Zoom today, as people were joining, I had a couple conversations with folks who have ties to this plant even back to the 40s. And I feel like a lot of the people I meet here have a similar story. So I feel like this should hopefully be interesting to you and maybe tell you a little bit more about this plant that is a big part of our community. So yes, I'm the Director of Process Development for SMC, and that's in our Research and Technology or Research and Development Department. And that our group it sits in Huntington, but we actually support SMC worldwide and also a lot of PCC companies. You find in manufacturing these days, R&D, unfortunately, in the US, is when cost-cutting measures are coming up, they're typically the first ones to go. But if you think about the groups and the technical power that's going to help drive companies to be competitive in 5 years, 10 years down the road, that's really the purpose of R&D. And so luckily, PCC and Special Metals understands that importance. And so our group is actually growing, which is good. So just a short bio to kind of go a little bit beyond what the introduction sort of told about me. So I'm from Michigan originally, outside of Detroit. And I got a bachelor's in metallurgical engineering from Michigan State. And that's kind of where I first learned about what's called material science. And metallurgical engineering is just a part of material science, just focused on metals and their alloys. But that's a hybrid between mechanical and chemical engineering. And my first introduction to nickel alloys actually occurred there with a material called nitinol. And it's actually 50% nickel, 50% titanium. And it exhibits some interesting properties, namely shape memory and superelastic properties. Shape memory, it's actually used in cardiovascular stents. So you make essentially a wire tube, and if you manufacture that at room temperature, it's smaller. And if you insert that into the body, it heats up and expands. So that really started getting me fascinated into material science, and kind of led me to want to go into graduate school, which I went to Virginia Tech, and that's where I met my wife, Dr. Lynn O'Connell. She works at Marshall and also the School of Medicine. But the interesting thing is, even though I'm not from here, I actually have some family ties to this area because her parents are from Northern Ireland, but they moved here in the early 80s. My father-in-law is a civil engineer, and he actually was brought over here to export coal back to the UK. He worked in the coal exchange building, actually. And so they were here for about 4 years. They lived in Timberlake, and then they moved to DC, which is where Lynn was born. And then I met Lynn at graduate school, and then I got a job here in 2014. We had a son not too long ago, about 7 months ago now. And then because her parents are now grandparents and they wanted to be closer to our son, they moved back to Huntington around December of 2020. So about 40 years removed, they came back. So I thought that was an interesting story to share. So the agenda for today, I wanted to talk about the early years of this place, which is called the nickel plant around here, and then get into the creation of what are called superalloys, and then go into a little bit of Special Metals Corporation and PCC and how that kind of came about, and then the applications of our materials. So starting back at square one, INCO, or International Nickel Company, that originated from the nickel mines in Sudbury, Ontario. And the Canadian Copper Company, working in partnership with Orford Copper Refinery, established a monopoly of these deposits in Sudbury. There's a sort of a graph that up there on the top right that kind of shows, it's an intensity plot of where actual nickel copper ore is actually enriched or not. But anyways, in 1902, the American banker J.P. Morgan, and also Charles Schwab of Carnegie Steel, along with those two companies, sort of helped merge and form the International Nickel Company. So that was in 1902. But what drove the manufacture or the building of this plant was actually a material called Monel. And the patent for Monel was filed in 1905. And this material was patented by Ambrose Monel. And Monel is essentially 66% nickel, 34% copper, and it actually mirrors the composition of the ore that's found in those Sudbury mines. And we have since trade named that and patented that alloy as Monel Alloy 400. And the significance of that alloy is, to this location, is that INCO wanted to mass produce and commercialize Monel metal, as they called it. And this facility was built in 1922, and it was built after the nickel market collapse following World War I. And they built it to overcome challenges they had with shipping material to steel producers. So they would ship the raw material to steel producers in New York for conversion. And so they kind of wanted to have control over that themselves because of the challenges they were having. And so they built this facility, and at the time, and it still is, it's the largest facility in the world for producing nickel-based materials. And they picked Huntington because it had a skilled workforce, excellent transportation and shipping, being that we're right on the Ohio River, and also an ample natural gas source. Because our materials are so strong, you need to heat them up to really high temperatures, sometimes 2000 degrees Fahrenheit or higher, in order to convert them into something that resembles, a wrought or a shape like a plate or a bar. And I found this really cool article from the third quarter of 1922 that kind of was describing, why they picked this location. So I thought that was a really cool piece of history. And then I dug a little deeper and I found some more really interesting photos of this plant. So this photo on the left is from the third quarter of 1922, an aerial view of the facility at the time. And then on the right, this is the fourth quarter of 1922. It's a cartoon, pretty nice drawing actually of a 7-ton electric arc furnace tapping one of the first heats of Mon-El metal. I found another cool photo here. This is from this is of the rolling mills of this facility, but it's from the Chesapeake and Ohio mainline tracks. Pretty old photo. And then another one here, this one's from August 23 of 1922. It looks like they're just kind of cleaning some of the finished products. That's done in a much more automated fashion now, as you can imagine. And another one, so here's, this is a 25 ton. So a ton is 2,000 pounds. So that's a 50,000 pound capable open hearth furnace that they're tapping some molten material. And this is from May 27th of 1922. This is the 30-inch hot mill and sheet furnaces. And another photo I found, this is sort of at the end of the line. So they're actually sort of cutting these sheets of Mon-El to final size, and you can see that they're packaging them up for shipment. And this photo on the left, it's from the first quarter of 1923. So once you melt material, you got to be able to, kind of form it into a shape, right, that's usable. And so this is actually a hammer forge that you can tell is very manual intensive and requires a lot of operators to actually work. We have a hydraulic open die forge press now that is more computer controlled now than human. And then the photo on the right, again, is just another cool photo I found in the archives. So some early applications that Inco was touting. So actually at that time, nickel, they were calling it nickel steel here, Mon-El was actually being used in the construction of bridges. So this is the Quebec Bridge over the St. Lawrence River. About 16,000 tons of nickel steel, as they were calling it, were used. But in the middle there, I found this really funny. The marketing team was touting that Mon-El could be used in golf clubs, weed out the duds, put in new Mon-Els. And then on the right, Mon-El is actually being used in the manufacture of Campbell's soup because Mon-El is very corrosion resistant and doesn't oxidize, and is very good for to maintain a clean environment for cooking. And then after a year of this plant being around and in operations, the stakeholders had a meeting on site, and I found in some of our old literature a report of that meeting, and I kind of highlighted a quote that I found was very telling, and actually I would call it a premonition that came through. They said the growth of the use of Mon-El metal has been tremendous, and each month new possibilities develop. This will undoubtedly also prove true on rolled pure nickel, which is a comparatively new product insofar as it has been available in any quantity on a commercial scale. In spite of the above, all at the meeting were convinced that the use of both metals is still in its infancy. And that was, I thought, very interesting because it couldn't have been more true. And so jumping forward to the 1940s, we call this decade the birth of superalloys. And this area of development, or this time frame of development and innovation, was really spearheaded by the gas turbine engine. And I found this quote from the Committee on Gas Turbines from 1940 in June. "The present internal combustion engine equipment used in airplanes weighs about 1.1 pounds per horsepower, and to approach such a figure with a gas turbine engine seems beyond the realm of possibility with existing materials." And that's because at that time they were using all ferrous materials or steels. And so little did they know, a guy by the name of Sir Frank Whittle was actually patented a turbine engine that actually used nickel alloys in its design. It was patented in 1930, and the first flight was in 1941. And you can see a photo kind of in the middle right of that first demo engine. But this engine required materials that could withstand very high temperatures. And that's where nickel comes into the equation. At that time, all the castings to manufacture those high temperature components were done in air. Nowadays, everything's done, all the premium quality materials actually vacuum melted because oxygen is not good for high temperature ductility, or the amount of how much material can flex. And so one of the key alloys that was developed during that time was Mnemonic 80 by a guy by the name of Leonard Feil, and he invented that alloy. And I show a table here on the bottom, just kind of showing some of the compositions. We're not going to get into a lot of the metallurgical principles here, but I wanted to highlight the first two alloys. There's a Stay-Blade steel and Rex 78. The highlight there is that those are both iron base, and they have chromium for oxidation resistance, and some of them had some nickel. But Mnemonic 80 was different, and then nickel was the balance element, meaning the majority of that composition. And then there's some other elements that were added for strength. But that switch from an iron base to a nickel base really helped drive the evolution of the gas turbine engine that's used in aerospace and in planes that you fly in today. And then jumping ahead about 10 to 20 years, 1950 and into the 60s, we call this era the era of alloy development, because now we're using nickel-based materials, but what they were doing in this decade was actually designing those materials, those superalloys, based on the specific performance that component needed in practice. And so we have the blades and vanes of the gas turbine engine, the rotors, which are a rotating component, and then other fabricated parts. So we were designing alloys with the properties and the requirements in mind. And then we learned about these two strengthening particles in nickel-based alloys called gamma prime and gamma double prime. And I have two photos on the bottom right, which they may be hard to see depending on how large your screen is. But I wanted to highlight that these particles that are innate to these materials, these nickel-based superalloys, are on the order of nanometers, or one of them can be on micron scale. So 1 micron is 10 to the -6 meters. And so to put that in perspective, the human hair is about 70 microns thick. And a nanometer is 10 to the -9 meters. And some of these particles are of that length scale, but they're a huge contributor to nickel-based superalloys' ability to maintain strength at very high temperatures that are seen in the gas turbine engine. And so some of the prominent names of this time, Herbert Eiselstein, he actually lived in the area and was, I think he ended up, his office was about 3 down from where mine is now. I'll get back to him in a second. And then also Clarence Bieber. Clarence was the inventor of several alloys for the gas turbine engine and also the Apollo moon vehicles. So those two guys were really the fathers of this era of alloy development. And during that time, the most popular and still the most widely used nickel alloy today, Inconel alloy 718, was developed because it was very high strength. We were able to weld it to other materials. It was readily formable, and it was cobalt free. Cobalt free was important because the price of cobalt is normally 3 to 4 times the price of nickel. And so from a cost perspective, if we were able to get cobalt out of the alloy, that was a good thing. So Herb, he developed 718 and 625, which still today at this plant are the two most common alloys and the highest volume for us. And he also developed several other alloys that we still produce today. And here's just a chart showing at the very top left, 1905, that initial patent of Monel alloy 400, and then going through the years, and the bottom right, 2009 was our last significantly patented alloy of Inconel alloy 740H. And our group here is still, we still have a few inventions up our sleeve. So I wanted to move in now, since I kind of set the stage of the history of Inco, how Special Metals works into the mix. So Special Metals today has 4 main facilities across the world. We have the New Hartford, New York facility, which is near Utica, upstate New York. It's about 42 acres, about 400 employees, and there's a supporting site nearby called Dunkirk. Then we have the Huntington facility, which is the largest, excuse me. It's 140 acres. Around, at the time now, we have about 900 employees. I think several decades ago, I think we approached close to 2,000. But we have supporting sites in Bernal, Kentucky, which a lot of our manufacturing processes involve both Huntington and Bernal. So there's material always flowing back and forth between those two sites. But we also have 2 other smaller supporting sites in Elkhart, Indiana, and then also Newton, North Carolina. And then in the UK, there's the Hereford facility. It's 47 acres and about 650 employees. It's about 2 hours north of London. It's kind of in the English countryside. It's a really cool place to go to. I've been fortunate enough to go there about a dozen times. And then we have a facility in Perth, Australia, which is on the western side of Australia. It's much smaller. It's 10 acres, 100 employees. And there's a supporting site called Overall Forge, which is actually on the eastern side of Australia in Albury. And so I wanted to kind of show via a timeline how Special Metals and those plants kind of became under one umbrella. So I have kind of 4 rows here: Huntington, Hereford, New Hartford, and Wausau. And so in the 1950s and 70s, the evolution really started in that in 1954, Hereford was actually commissioned. And then in 1956, International Nickel or Inco acquired Hereford. And then moving a few years in advance, we have 1960, Special Metals buys New Hartford. So Special Metals was not linked to Inco at all at this time. And then moving on to the 80s and present, in 1994, there was a joint venture of a few different companies, including Pratt & Whitney Aerospace, that formed Western Australia Specialty Alloys, or WASA, which is the Australian, or the facility in Perth. And then in 1998, Special Metals Corporation bought Inco. So at that time, the New Hartford plant was Special Metals, and they bought Inco, which included Huntington and Hereford. So that was the big merger. And then in 2002, you start seeing this name called Precision Castparts Corporation. They were not linked to Special Metals at the time, but they bought WASA. And then in 2006, PCC, or Precision Castparts Corporation, bought Special Metals Corporation. So in 2006, all 4 of those companies that now are SMC were acquired. And so Precision Castparts Corporation, you probably don't hear that name around locally, but PCC is sort of our mother company. And that actually started in the early 80s and evolved over time. PCC's mantra is growth by acquisition. And so when PCC grows, it's buying other assets, other companies to kind of create a vertically integrated supply chain to the end user, starting from the mining industry to special metals type companies where we're taking the raw materials and forming them. And then special metals will supply it to a company that focuses on making specific components. And then those components are then sold to the Airbus, the Boeing, the Pratt & Whitney, the GEs of the world. And so you can see just by this chart here, which is in sales in millions of dollars, you can take the first number and just say billions. So it became a very fast growing company, especially in the late 90s and into the mid 2000s and to where we are now. And then as it was said at the beginning of this talk, in 2016, Berkshire Hathaway purchased PCC. And so PCC is now no longer a publicly traded company. So our financial information isn't disseminated quite like this anymore. And so PCC is actually broken up into 3 operating segments. So we have forged products, airframe products, and investment cast products. Special metals is part of forged products, which is the biggest chunk of the pie. It's about 43%. And then our forged products includes a few other companies. And so our particular branch of forged products is called the PCC Metals Group. And that really involves special metals, TiMet, which is the titanium producing equivalent of special metals, and a few other companies. But PCC as a whole, as far as the industry served, aerospace is the big one. It's 70%. And then 17% power, then general and industrial and other markets. But Huntington is actually much more diverse. There's more pieces of the pie there. And so during the pandemic, as business is starting to rebound and people are starting to fly again, there are other parts of PCC that were more tied to the aerospace industry that were hit much harder than Huntington. Huntington, we serve many other markets, which I'll get into in a moment. So Huntington Alloys today, it's still the largest fully integrated nickel alloy facility in the world. And what we offer are what we call raw mill forms. So we supply ingot, which is just a cast product, typically either a large cylinder or a rectangular casting. And then we would sell that to someone to convert it down into something else. But we also sell other products that are closer to the finish line, like just plate or sheet products, rod, which is just a bar, different sizes. We also produce wire that can be converted down into a welding product to weld nickel alloys to steels or other materials. We also produce tube and pipe, which are huge in the petrochemical industry and the oil and gas industry, which I'll get into a little bit. But going back to the markets that we serve, so oil and gas and power generation or energy are actually the biggest markets that Huntington supplies. We do supply aerospace, but there's other parts of special metals that are more focused in aerospace. And then just the general processing industry, and then refining are the other markets that kind of sort of hit the whole gambit. And then the supporting operations I mentioned a little bit earlier. So we have the plant in Bernau, Kentucky, that has some of our melting capabilities, air induction melting, and one of our remelting operations. And then all of our tube and rod extrusion, that's a process we have here, is housed in our Bernau facility. In Elkhart, Indiana, that is all just really thin sheet. So I'm talking about 0.05 inch thick sheet. And so the feedstock that feeds that mill comes from Huntington, but we can't make as thin of sheet as they can. So if we have orders out there for really thin gauge stuff, we'll send our sheet to them and they'll cold form it down to something a little bit thinner. And then we have the welding products facility in Newton, North Carolina. So they will take a wire that's produced from Huntington, and then it's very much like Elkhart for the sheet side. They will take our wire and draw it down to something like 1 millimeter or really small diameter wire that's used for a welding consumable. So I wanted to get into some of the technical aspects of nickel. Well, not a lot, I promise. I just wanted to introduce you to nickel itself and kind of the history and some of the properties of it. So I guess in the 1700s, German miners actually uncovered an ore resembling copper, but they were not able to extract it very easily. And so they blamed evil spirits and dubbed it the ore Kupfer nickel. So Kupfer means copper and nickel actually means bad spirits. And then in 1751, a Swedish mineralogist, and I will not attempt to pronounce his name, he actually extracted the silvery white metal, and he was the first one to uniquely identify it as nickel. And actually, it's the 5th most abundant element on Earth, but most of it's in the Earth's core, greater than 1,800 miles below the surface. And this table on the bottom, I kind of show nickel compared to some other structural metals that you probably have heard of, like iron and titanium. So nickel is actually the most dense, meaning for a given unit volume, it's the most weight. And it actually has the lowest melting point, which is interesting. And another interesting thing about nickel, as far as things you would encounter on a day-to-day basis, so our nickel coin, contrary to what the name is, it's actually only 25% nickel. It's the other 75% is copper. Another interesting fact is that the majority of nickel is used in stainless steel production, not nickel-based superalloys. It's because the volumes in the market out for stainless steel is much more vast and a lot higher than nickel-based superalloys, because superalloys, you only use them when you have to. And you have to do that when iron-based materials like stainless steel just can't hold up to the application. So I'm talking about very high temperatures or very corrosive environments. And so therefore, the nickel prices always align with steel demand, and they oftentimes reflect the state of global manufacturing. So I have a couple plots here on the right just showing the production of nickel in millions of tons per year. And so you can see since the 1920s, when this plant was commissioned, it's sort of on an exponential increase to where we are now. And then also on the bottom right, I show the dollar per pound of the nickel price. So traditionally, it's hovered somewhere around $8 to $7 to $6 a pound. But you can see in September, late 2006, it had a huge spike up to about $24 a pound, which was great from a nickel producer perspective, because we can add margin on that for our products. But that was due to China really revolutionizing their manufacturing. And so there was a worldwide shortage in nickel. And so the nickel miners were able to tack a big premium onto the price of nickel. Another fun fact, so beer kegs are made of nickel-bearing stainless steel, and they often stay in use for about 30 to 40 years because of their corrosion resistance. So I wanted to get into some of the applications of nickel alloys and why nickel is actually used in them. you only use nickel alloys in applications that demand very high temperature mechanical or strength and or very high temperature conditions that you need some specific thermal properties. So like oxidation resistance and also corrosion resistance. And that can be at high temperatures or at low temperatures. And I'll get into the low temperature application in a second. Then also for conductivity. So nickel-based materials have really good thermal conductivity and electrical conductivity. Ferromagnetism, that means being non-magnetic. So iron-based materials have something that's called a Curie temperature, and being above or below that determines whether that material can be magnetic or not. So these are very specialized applications, mostly in the electronics businesses where some nickel alloys are being used. But the primary markets are aerospace, power generation, oil and gas, and then just the processing industry. And I have a pie chart up on the top right kind of showing the breakdown of the different markets and how much volume really goes into those specific markets. So I wanted to kind of just give some examples how nickel alloys are used in these particular markets and industries. So the aero and industrial gas turbine. The plot on the left is kind of showing where all of the different PCC companies are manufacturing components that are nickel in the gas turbine engine. So PCC, given that it's 70% aerospace, has their fingerprint all over that engine. And every single plane that you've ever flown in has components made by PCC in it. And on the top right kind of shows some of the alloys that are used in the different components. Most of these alloys are actually made here in Huntington. Some of them are more delivered in a cast condition. And so there's a division of PCC called PCC Airfoils that focuses on those. But on the land-based gas turbine engine side, so the gas turbine that's not going into planes, I have a photo on the bottom there. That's a GE, a General Electric land-based gas turbine engine that is one of the biggest products that we produce in Huntington. We make the big turbine rotors that goes into that engine. And the finished component is about 100 inches in diameter. And the casting that we supply to another PCC company to make that is about 30,000 pounds. So it's a very big product for us. And then I wanted to talk a little bit about the oil and gas applications. So these are much lower temperature. And so nickel alloys are used for a completely different reason. It's mainly for corrosion resistance and low temperature, high strength. So nickel alloys can be heat treated to really high strengths. And then also having very good corrosion resistance. So this photo on the left is sort of a schematic of a subsea oil and gas extraction unit. And the very top of it is the sea floor. And there's all these different components. And you can see there's several different alloys that are being used here. 718, which I mentioned is the most common use nickel alloy, but a bunch of other nickel alloys, and they're engineered for different purposes. And so as you start going further and further down below the sea floor, the environment becomes more and more extreme. You start encountering higher pressures, higher temperatures, because you're closer to the Earth's core, but also hydrogen sulfide starts to enter the mix. And hydrogen is an embrittler, or something that degrades the materials of steels very readily. And so nickel alloys have much better hydrogen embrittlement resistance. And so you use some very specialized nickel alloys for really, really low or very deep depths below the sea floor. On the right here, I'm just showing some of the alloys that we produce here in Huntington. Well, I'm showing a 945X blowout preventer. So this component actually, if something goes wrong in that downhole string and there's a fracture and there's danger that some of that oil and gas that's being extracted is going to go into the ocean, this component just shuts off the entire system. So it has to be very high strength. And that's the safety valve flapper is part of that blowout preventer. But that was produced from tubing and bar product that was made in Huntington that was sent to someone, and then they machined out these components. And so this is a graph kind of illustrating what I was talking about. So at the very top part of this chart, you see carbon steels, and these are used in oil and gas applications where the temperatures aren't very high, the pressures are not very high, there's no hydrogen sulfide in the environment. And because carbon steels are cheaper and the environment allows for it, you want to use carbon steel. But as the temperature increases and the pressure increases, the environment gets more extreme. You start moving away from carbon steels, you get into the stainless steels, but after a certain point, they can't handle it anymore. So you start getting into some Mon-Els, then you start getting into even further down, the very corrosion resistant nickel alloys like 725 and C276. And those are actually very expensive, and because they have elements like molybdenum in them for that corrosion resistance. Some other applications, so just general thermal processing. Nickel alloys are used in furnace retorts and muffles, radiant tubes and furnaces, rotary kilns, just wire baskets for holding material that are going to be heat treated at high temperatures. So if you made this wire basket out of a steel, you might be able to expose material at high temperatures maybe a couple times, whereas nickel alloys, an apparatus such as this could last several thousand cycles. And then the petrochemical and processing industry. So on the left is a gas heated reactor, and it incorporates nickel alloy 693. So Huntington actually supplied this project with sheet, plate, and tubing. And then in the center, we have just a tubular heat exchanger. Our materials are used in hydrogen reforming units. And on the right, I show a zoom in on some hydrogen reformer pigtails that are made of Incalloy alloy 800H/HT, which is a high iron nickel alloy that's designed for high temperature oxidation resistance and strength. And then some other applications. This one is a relatively new one. It's called AUSC, which stands for Advanced Ultra Supercritical CO2, coal-fired technology. So this whole effort was trying to make coal-fired technology more efficient, and that was to create steam at a very high pressure to increase the efficiency of the energy that's produced. And the takeaway here is that the only materials that can sort of give you this technology or help this technology become realized are nickel alloys. And I show a photo on the bottom left. So this was material that was melted and forged to a cylinder or a rod in Huntington. And we sent it to another PCC company called Wyman Gordon in Houston, and they hot extruded this pipe of Inconel alloy 740H, was one of our newer alloys. But at the time, that was the largest nickel alloy pipe ever produced. So it was about 15 inches in diameter, and the wall thickness was 3.5 inches thick. We've since surpassed that actually about a year ago. But this technology, even though the US seems to be moving away from coal-fired power plants, this advanced ultra supercritical CO2 concept is being used in more greener technologies as well. So it's even though the concept was designed for coal, it can be adapted to other energy generation technologies. So that's kind of the what I wanted to sort of cover today, and I think I left enough time for some questions, but overall, what we call the nickel plant it's really been a significant contributor to the growth of the aerospace, energy, and chemical industries. And actually, next year will be our 100th anniversary, which is really exciting. But SMC in general, because we serve a very diverse customer base, I feel this plant in particular is very well positioned for the future, because the technologies in aerospace, power generation, and even solar energy, they're moving towards higher temperatures and more extreme environments. And that's where steels and other alloys will just fall short. So that's very good for the outlook of this plant. And for that reason, Huntington, the plant here, will continue to be a key business and employer for this area for years to come. So that's all I had for today. And I really thank you for your attention. And I think if we have some time, we can talk through any questions you might have. So thanks.
Thank you, Dr. O'Connell. I've enjoyed this presentation twice now. I think that Inco and now Special Metals has been a huge staple for our community and our state. And I'm amazed at all that the company does and has done. And so now I would like to open it up for questions. I can't see our people with the screen sharing. Do we have any questions for Dr. O'Connell? There we go. Now I can see everyone. Thank you.
I told you I'm not a professional Zoomer. So give me a second.
I'm not either. I'm not either. It's a baptism by fire for me. Thanks to Eric, I look professional. So do we have any comments or questions? Betty, you are muted. Hit your space bar, Betty. There you go.
I have a question. Okay.
As we said before you started, we're interested in the nuclear atomic installation there. Is it still there, and what is it doing? What did it do?
Yeah, so what Betty's referring to is this plant was actually very much involved in the Manhattan Project. So trying to figure out what to do with nuclear waste. And that part of the plant no longer is active. And because it was so long ago, and some of the people that were active with that are no longer around, or are still not employed here. Some of the knowledge of that time is it's not very well documented, and I think probably for for reasons that are I can understand. But no, I mean, to answer your question, no, that part of the plant is no longer operational. I know that the EPA and other government agencies have sort of audited the radioactivity of where that part of the plant was. And so I've not heard anything bad from that. So I feel very safe here. Yeah, so I don't know too much about it. And I actually, a couple months ago, when I gave the Rotary Club presentation, someone else asked that same question. So I started trying to get some questions answered myself, and I didn't really get too much of note, but yeah.
I understand it was all secret.
Yeah.
So a lot of the waste, including the pencils, were taken to Waverly, Ohio, and buried. Yeah.
So a guy who actually sits right next to me, some of you may know him. His name's Jack DeBarbadillo. He, Inco, when they shut down their research lab in New York, a bunch of those scientists came to Huntington, and that sort of founded the R&D group, or research and development group here. And Jack came over here in 1984 when that lab shut down, and he is 82. he is still full-time. And so when I was thinking about someone who might have knowledge, that's who I asked. And so he said, there was people who are still active from that time period. And they were still in their, still working here in the 80s. And so he actually tried getting some information out of some of those people and over a beer, and he wasn't able to get much.
Yeah.
Well, that was a wonderful presentation. Thank you so much, Dr. O'Connell. Just the appreciation that I know that a lot of us have about a significant industry and plant and in our city. I happen to just a personal interest story about just the history of people and working at Special Metals and Inco and the nickel plant. I had the opportunity to serve as the interim pastor of Beverly Hills United Methodist Church, which of course is up Washington Boulevard. And I was humbled to have a funeral of a man who lived in Gallier Village, when Gallier Village was what it was in terms of just up the hill out of downtown and it's all of its history, but every day walked to work with his lunch down Washington Boulevard to the nickel plant.
Yeah.
And then back home. I remember so vividly his widow sharing with me that story and then some of his family around their dad having that kind of experience. And that to me, and so, I mean, just hearing you today and putting that history and the just where we are here in 2021, that this plant is what it is. It's just amazing. So I just kind of wanted to give that little, the human interest part of that with people who've worked there.
Yeah, I mean, that's one of the really cool things. I didn't know what I was getting to when I decided to take a job in Huntington, West Virginia. I just knew that this plant produced metals and I was a metallurgical engineer. But that is one of the really awesome things about this place is the history and also the fact that most people I meet out in the community, much like the person you're talking about, has ties to this plant. It's really cool.
Well, if you just drive down, I mean, think about Gallier Village and right there where the 911 facility is, and he lived up in that area and walked every day down to the plant.
Yep.
I was just amazed about its connection.
Yeah.
Dr. O'Connell,
Mhm.
I would like to just say I thoroughly enjoyed your presentation.
Well,
And
thank
on
you.
a personal note, and we all have personal notes about the nickel plant, but my father and my uncle both retired from the nickel plant. And when I was a very young girl, I thought my daddy made nickels there, you see, because daddy always had a roll of nickels. So that was just a fun little thing when I was little happen. But my father and my uncle both retired from there. Made a very good living there.
Good. That's good to hear.
Thank you.
Any other questions or comments for?
Dr. O'Connell, I wonder how you see the future of the plant. And I mean, people have talked about its heyday and then it went downhill, then it seemed to resurface. Where is it now and what do you see in the next 5 years or so?
Yeah, I mean, that's a great question. Yeah, I think the reason that I think at our heyday, we may have been up to 2,000 or more employees. Now we're under 1,000 is because of our competitors and also a lot of competition overseas. And I don't know if you remember that slide I showed where it had sort of our patents that we had by year, starting back in 1905 from Monel, even as late as a few years ago. So when you patent an alloy, you only have coverage for 20 years. So the vast majority of those alloys on that list can now be made by our competitors. And so that takes away, we have technical expertise in how to produce those materials, but it's only a matter of time when our competitors can legally make the composition, figure out how to process it, and then you have competition within the market. And a lot of our competitors don't like to be tied to one supplier for risk mitigation reasons. If someone goes on strike and they're the only one who supplies this material to them, then they're in big trouble. So that's really what's driven the reduction in our volume overall. And so where we're trying to move towards in growing again is through exploring new applications for nickel alloys that are beyond just the traditional aerospace. So you think about electronic vehicles, there's application for our materials or new alloys that we can develop using nickel that could be incorporated into battery technology. There's also the solar technology world. I don't know if you've ever seen, but there's a place in the southwest of the US called Crescent Dunes. And there's other, in the desert type environments, you see these things called concentrated solar power plants. And what they are is they're a field of mirrors that are all reflecting the sun up to a central receiver. And that receiver is taking that solar energy and it's transferred through a hot molten salt, and it's transferred through nickel alloy tubing. And that molten salt, which is over 1,000 degrees Fahrenheit, is then put through a heat exchanger that is heating up and making steam, and that steam is powering a turbine to generate electricity. And so there's a whole area of that technology that's it's not mature at all. And so we're actively developing either applications or materials for that technology. So we're trying to get out of the commodity type businesses and getting more into the newer technologies that show to have promise in the next 5-10 years. But at the end of the day, since a lot of the materials we produce are off patent, that just drives competition and that just takes away from market share. So we have to sort of reinvent ourselves. And so that's what my group's challenged to do.
Thank you. But when you do say competition, are you talking nationally, internationally, or with particular nations in mind?
All of the above. So we have our biggest competitors in the US are ATI, which is Allegheny Technologies Incorporated, and then also Carpenter Technologies Incorporated. But we have, our marketing team gets we buy into a company that does nickel alloy market research, and they give us a report. Special Metals used to be the #1 producer globally of all nickel alloy production. We are in certain areas still, but other areas, particular product forms, there's companies in France and then also in Germany that have overtaken us. And then China is starting to really take over in the Far East markets. So Special Metals actually has a sales office in Singapore that helps us have contact with China and Japan and Indonesia. And so China's realized, well, we can start making these materials and cut out the costs of having to ship nickel alloys from Huntington to Japan, right? So it's really a global competition environment. So we have US competitors, and then, like I said, France, Germany, UK, and in Asia.
Thank you.
What is the age of a patent in that industry?
Yeah. So 20 years. So from the time that you file or you have what's called you essentially start that process until it's granted. Once it's granted, you have 20 years of coverage, meaning no one can legally produce that material, and definitely not sell it. You can't even melt that composition. But after that, it's fair game. So, but the part of the thing that's part of the problem of that is, so if, let's say you take the nuclear industry, to come up with a new alloy, okay, you have the patent, you're covered for 20 years, but to actually get that material qualified and spec'd into that application, it might take more than 20 years. So you're essentially doing everyone a favor by designing an alloy, patenting it, and then you're doing all the work to get it spec'd into the nuclear application. And then by the time that's done, someone else can just produce the material and it's already in the application. So that's the challenge. Whereas other markets like oil and gas, the barrier to entry is much lower. So we've patented alloys and have had them spec'd into the application within 5 years. So once that happens, we have 15 years of coverage. So we're the sole supplier. And we have a few different alloys that are still in that situation. So it's really market driven as well.
Do you have any other questions or comments? And I do have a question. Are you going to have a big celebration for your 100th year anniversary?
We are, yeah. There's not any concrete plans. There's ideas and sort of segmented plans, but yeah, they're going to have a big thing here, and I think invite a lot of the community as well. There's sort of preliminary ideas, but nothing formal yet. But yeah, that's definitely in the works.
Well, any other comments? Go ahead, Betty.
I was not aware that there was a connection with Berkshire Hathaway.
Yeah.
And I wonder, that sounds like a compliment to the company, because they seem to buy successful companies. But I wonder if their ownership has made any difference in the operation or the amount of research and development money that might be available, or anything that has caused.
Yeah, that's a very good question, Betty. So yeah, it has made an impact. When you're in the, they tout it a fast-paced manufacturing environment. There's a lot of pressure, and when you're a publicly traded company, a lot of that pressure is derived from where the market analysts kind of see your stock price going. And that's tied to your quarterly performance. And so that in itself drives, pressure. But now that we're owned by Berkshire and we're now a private company, those pressures have subsided a bit. But you brought up another good point in that Berkshire and Warren have, pretty deep pockets. And so when there is something special, or, when we are making capital appropriation requests for getting new technology, new equipment or what have you, it's a lot easier actually. And I think there's just an overall bigger budget for that type of stuff than there used to be. And so the challenge with hunting this plant in particular is it's a big plant. It's old. It's been around for a long time. So you got to pick where you want to make the improvements, because just to improve one department, you're talking about tens of millions of dollars potentially. So you got to start somewhere, right? And so we have made a lot of improvements over the last 10 years, even though the outside doesn't look like it. But a lot of our competitors are putting in state-of-the-art of equipment, and we got to keep up with them in order to stay alive, right? So, I mean, we're very cognizant of that. But yeah, with Berkshire, I think it's been a good thing overall for PCC and this plant in particular.
Any other comments or questions for Dr. O'Connell?
Well, I think not so much about Inco, but you said, well, you ended up coming to Huntington. That didn't sound like that was a plan for any particular reason. And I'm wondering, as a young professional, how you found Huntington. Is it what you expected or better than expected? Comments?
Yeah, good question. Yeah, the reason, so my wife was still in her graduate program when I finished, and I knew I didn't want to go into academia. No offense for the professors on the phone if there are any, but because I had very much seen that world was not for me, and I liked seeing the things that I was doing make an immediate impact, and that was the intrigue of industry for me. Now I still get to work with universities and government agencies, so that's cool as well. But so the reason I moved here was PCC actually sponsored a building at Virginia Tech and actually helped bring it online. And so I kind of knew about PCC and Special Metals. And since Huntington was only a 3-hour drive from Blacksburg, where Virginia Tech is, I was like, oh, this sounds like an interesting opportunity. I don't know much about the area. I didn't travel here before I took my interview. And I was like, well, it's 3-hour drive. The job sounds really interesting, so I'll take it. And then my wife and I did distance back and forth for about a year, and we just grew to love the area. And since I moved here in 2014, this Huntington has dramatically changed. The restaurant industry has, just boomed. I mean, every weekend in downtown Huntington, there's something you can sink your teeth into, whether it's different concerts or, the Chili Festival. I mean, there's just an innumerable number of things to get your teeth into. And I never really liked the big city life. So for me, it's a good sort of hybrid between, there is a city feel in some aspects, but it's also, you can get a suburban feel as well. So no, my wife and I, we're not from here originally, but we're here to stay. We like it here.
It's great news.
We need people like you to come to our area and love it and bring your talent and your education and your good thoughts and your good vibes. So we're glad you're here. We had where my husband and I lived when we first got married. There was a couple that lived on our street, little cul-de-sac, and he was actually from England and came over here to work for Special Metals and worked over here until at which time he retired. So, and then Caledonia Metals bought the house across the street from us, and their executive, the president would come and stay from time to time. So
okay.
I feel like I have a lot of, and of course I said my father-in-law was retired as an engineer from Special Metals. So as you say, we all have stories about Special Metals and formerly Inco. And I'm just glad that it's still thriving. I think we all can agree that we're very, very thankful for Special Metals. Any other comments or questions?
May I tell you about a poster that my husband especially liked? And it quotes the head of the U.S. Patent Office in 1899 as recommending that the office be closed down because everything that could be invented had been invented. Can you believe that?
Yeah, there's even in there's a lot of that. You see that actually in the aerospace industry. They thought nickel alloys had reached their maturity, and no more improvements or innovation could be had with nickel-based materials. So they thought they were going to have to go to ceramics, which are very high temperature materials, but very, very brittle. But that literally died in the 90s. And, there's tons of examples like that where people are like, there's no more improvements to be made. Let's move on to something else. And, some new technology comes up that enables something that you never thought possible. That's what I like. That's why I like being in an R&D environment, is because I'm tasked to kind of think that way. I'm supposed to be thinking of the pie in the sky idea. So yeah, there's tons of examples like that.
Any other questions or comments before we leave today? I don't think we have any. Again, Dr. O'Connell, thank you. I enjoyed the presentation. Again, I was lucky enough to hear you at Rotary and kind of stole you away from Rotary.
Yeah.
But thank you for being here, and thank you for all that you do for our community and for Special Metals to keep it going, because we need Special Metals to stay and be vibrant. There's no question about it.
Well, I appreciate that, and it was a pleasure to talk to you guys. And like I said, I was excited to learn about this program, and I definitely know of a few people who I think would definitely like to join. So
please email me. I'll email you my phone number. So if you would like to call and talk about it, but please, we love recommendations. That's how we grow. That's how we grow. All right. Well, thank you again, everyone. Have a great day, and we'll see you soon.